Welcome back, citizens, to the very basic refrigeration course. Now let's crack on and see how we go with the next lot. So, a quick review of the previous lessons. Hopefully we learnt that refrigeration is only the movement of heat from one place to another, and that also the work done in a refrigeration system is by latent heat. And that latent heat is the changing of state from gas to liquid or liquid to gas. Okay then, let's have a look at the refrigerant states within the system. They can be three states or phases of a refrigerant in the system. They are subcooled liquid, superheated gas, or a two-phase mix saturated. And this is actually the point where it's the transition between liquid to gas or gas to liquid. Okay, citizens, so here we have a diagram representing water at atmospheric pressure. Now you can see we have the two-phase mixture or TSAT line, as we've spoken about before. And because it's water and it's atmospheric pressure, that line is at 100 degrees centigrade. Or, as we called it before, the TSAT line, which is the temperature saturated line. Now, anything above that line, as shown by the arrow there, is called the superheated region. That means that there will be no liquid at all. It will just be gas, superheated gas. And as we said before, the opposite to that is if it's below that, it'll be below 100 degrees, it will be subcooled liquid. Here we have the same diagram representing the pressure temperature relationship for R22, and you can see that we have the same line at 0 degrees C and 4 bar G constant pressure. This once again we know as the temperature saturated line or TSAT. Now anywhere above the line we know is gas and superheated gas. So therefore if we were to measure that gas, the temperature, and it was 10 degrees C, we could say that it was 10 degrees C superheated. And on the other side, anywhere below that line is known as subcooled liquid. So for example, if we read that as measured that as -10, we would know that we have 10 degrees of subcooling. Okay, so here we have a bottle of refrigerant. In this case, it's R22, which of course is banned now and has been banned for many years, but it just shows you how long ago it was since I wrote this. So we have this bottle of refrigerant, and hopefully it's in equilibrium. That means that its temperature and pressure are correct. So we can take a peek inside the bottle, and you can see here we have refrigerant in a saturated or two-phase mixed condition. Now notice that there's liquid in there, and there has to be liquid there for it to be correct. In other words, you can't do the same with an empty bottle. And the pressure in the bottle will be dependent on the ambient temperature. And if we would take this bottle with the gauge fitted up to the Arctic, and at minus 41 degrees Celsius, the bottle pressure will be 0 bar G or 1 bar A. We'll try and explain the difference later. Now, if we were to take the same bottle to the Sahara at 50 degrees Celsius, the bottle pressure will be 18 bar G or 19 bar A. So, how do we work out what the temperature pressure relationship be? Well, you can do it by lookup tables. Here you can see a lookup table for R22 and a red line underlining 0 degrees C, and if you look carefully you'll see that there is a pressure of 497.99 kPa, so near enough 4 bar. Or you can use a comparator. In this instance we have one that lists the different refrigerants and the pressures on the side and has a temperature line in the center. So all you do is you set your desired pressure in bar A or bar G, in this case 4 bar G as we've been dealing with, and then go to R22 and look up and you've got approximately 0 degrees centigrade. Here we are again. You can see that this line here is the TSAT line. Again, showing the two-phase mix or saturated line. So therefore anything above that line will be superheated gas and anything below that line will be subcooled liquid. This is it, the Holy Grail. Good luck. Right, here we go. So here we have a bottle as shown before. Let's say the bottle temperature is 20 degrees centigrade, so the pressure would be 9.1 bar G. If we were to open the valve, this being the valve here, two things would happen. One, the F-gas police would come and arrest you, and two, the bottle pressure would drop. Now, as the pressure drops, the refrigerant wants to get back to the equilibrium again. It wants to get back to its temperature pressure relationship. Now, to do this, the liquid inside the bottle changes to gas, i.e. it boils, to make up the pressure by latent heat. In doing so, it needs to absorb heat, which it does through its surroundings, and in this case, through the casing of the metal of the bottle. So, we could end up with a very cold bottle and eventually no gas left. At atmospheric pressure, R22 will boil down to approximately minus 40 degrees centigrade. So, you'll end up with a bottle like this, with a nice frosting on the bottom where the liquid was. But once the liquid has gone, so will the cooling effect. Well, we could just stick a bottle inside a cabinet, run a pipe outside and release the pressure to achieve a cold fridge space. But the reasons why that's not a good idea is, again, the environmental police would prosecute you. It wouldn't stay cold for long. It would be very expensive. So what we need is a system that is self-contained and recycles the gas. Okay, we now know how to turn liquid refrigerant into a gas and at the same time absorb heat. This work is done in the evaporator, or in an AC situation, the indoor unit. Now all we need to be able to turn it back to liquid again. The next lesson will be on heat exchangers.